Welcome to this video. My name is Mark Scythian. The date today is September 18th, 2024. The title of this video is Electronic Chemistry, Quantum Technologies. So as of now, we have been using 2.4 gigahertz digital carrier signal frequency to transfer the liquid crystalline storage capacity of the water molecule. So the water molecule has the 10 resonant electrons, which have a resonant frequency of 2.4 gigahertz. So if we focus on the storage, information storage capacity for water molecules are enormous. So their complementary digital wireless frequency then supports what we call Wi-Fi. 4.0 gigahertz frequency is the complementary frequency of the iodine electron resonant frequency. And then of course we have the 60 gigahertz frequency for the oxygen gas electron resonant frequency, which has the capacity to transmit much higher or larger amounts of information over much smaller or less propagation range. So there's going to be very long wavelengths and higher frequencies. However, the practicality of 60 gigahertz in non-military applications is not practical. So really the scaling for civilian use is 29 gigahertz. So of course it's always a mathematical game to figure out where the numerics and parameters are practical for a given environment, but initially the sequencing was in the oxygen gas spectrum. So if we focus on the principle that wireless digital carrier signal frequency matched to a chemical compound's electron resonant frequency, chemical effects replaced electronically depending on wattage and efficiency. Thus then the focus is range attenuation minimized. So already in 2019 the frequency or frequencies given pesticide chemical compounds were successfully broadcasted into and across Texas in a controlled sector, approximately 20 gigabytes data per second from Washington State. And so the effect was congruent with chemical pesticides. Now the improvement would be not necessarily the thermodynamic loss of using a chemical, which more than 90% is lost in the transfer and heat exchange. And this is where we run into problems with potential genetic damage to the ecology. However, if a correlating frequency, which is what all chemicals do, a chemical is administered and then the electron resonant frequency changes and then the effect takes place. But much of the transfer is lost in heat exchange and has a very poor thermodynamic efficiency compared to electronic chemistry transfer or the complementary frequencies of the chemical in the form of a digital wireless signal. So this may improve on the ecological consequences. Instead, frequency disorientating devices or methods rather than the chemical dissociation of said biological creatures in nature. And so the R&D concept, which could be proposed, perhaps under research, perhaps not enough information right now, and this concept would be too fantastic but all science fiction can be made into science fact with enough information and research. So it is the rate of computational analysis that makes the fantastic technologies become economically viable and then worth investing in. So anything could be made possible. There's no such thing as impossible, but the economic practicality is what more or less holds back the great innovations. So we would take this concept of matching frequencies to chemical compounds, as already has been done in a lot of our quantum applications, cell phones, GPS, internet, etc. And so imagine this R&D, research and development application, broadcasting the frequency of hydrocarbon fuels as potential energy without combustion. So this would be a form of an electrostatic battery potential. So if we improve on this, we could then improve the proximity initially at closer ranges, hydrocarbon, electronic chemistry, laser transfer. And so of course, none of this transfer is free. It's going to cost perhaps more efficiency than makes this practical, but if the efficiency transfer is minimized under the conservation of energy, so there's going to be energy lost to transfer, propagate the frequency of, let's say, a material, hydrocarbon fuel, maybe CH4 natural gas methane would be the isolation medium, and then its electron resonant frequency transferred. And so the idea is to efficiently take the potential energy in the atomic state of the natural gas, transfer it maybe perhaps through a laser, and then have an endpoint receiver that would take the potential energy in another form. So we can't create or destroy energy, but we could change its form. And then the efficiency of laser transfer perhaps could extract the potential energy of, let's say, natural gas, CH4, methane, and transfer that digitally and electronically through perhaps a laser or perhaps a carrier signal or some type of electromagnetic medium, and then have a receiver endpoint that ends up converting that potential energy transfer into, let's say, electrostatic potential. So there's many applications that could take the potential energy of a substance, material, detangle, and then transfer it through energetic state back to a receiver, and then retangle or in quantum re-entangle back into a storage medium. So again, we have to look at the inherent potential energy of all materials and how we can transfer that potential energy either in structural strength, quantum electronic transfer, or of course combustion and heat. Thank you for watching this video and have a great day.